Hello everyone, I'm Xiaoling from the University of Hong Kong. Today I would like to introduce my work, Traffic Incident Detection, a trajectory-based approach. Incident detection is very important. First, detecting incidents can help dispatch medical and police resources immediately once they happen to reduce life loss. Second, users can be routed to incident-free passes to avoid congestion. This can not only help users to reduce their traveling time, but also can reduce the congestion further by dispatching incoming vehicles to other incident-free passes. In this figure, the user can avoid the path that incident happened. Previous work focuses on incident detection on road detectors on freeway roads. However, the coverage of road detectors is very low on urban roads, and the cost of traffic detectors are expensive. Recently, researchers paid closer attention to GPS-equipped vehicles to build traffic applications. It has two main benefits. First, it can be deployed without additional installation cost. Second, it's possible to cover a whole city. However, since many road segments are not covered by any GPS-equipped vehicles in some time windows, it leads to data sparsity on urban roads. Previous work on incident detection can be divided into three categories. First, pattern matching related methods. One most classic method is California. It calculates feature differences between downstream and upstream, then use threshold to detect incidents. Second, deviation detection-based methods. They are either focused on time series analysis or topic model learning. The main idea is to estimate normal distribution of feature from historical data, then compare the current distribution with normal distribution and use the deviation between them to detect incidents. The third category is supervised model. They treat incident detection problem as classification problem in machine learning. They use the features extracted from spatial temporal matrix to train machine learning model, then use the trained model to classify whether it's incident or not. We mentioned spatial temporal matrix in the related work part. You can see in this table, each cell represents feature value at the ith time interval and jth road. Supervised model I mentioned in the last slide often require a huge amount of traffic data over both spatial and temporal dimensions. They utilize the difference between spatial and temporal features to detect incidents, since these features deviate in a large degree once incident happens. However, not all spatial and temporal features differences may be available when only a few trajectories are contained in the dataset. For example, in Figure 1, only one trajectory is passing through the incident location and road R5 within 6 time windows, T1 until T6. Note that we can't obtain the spatial feature difference of road R4 and R6 and time window T2 because the features and cell T2 R6, T2 R4, and T2 R6 are missing. Our research question is, can we still detect incidents when trajectories are sparse in the spatial and temporal dimensions? This is the framework of our solutions. Our general idea is to look at the change in trajectories. Because vehicles affected by incidents have different patterns than those not affected by incidents. We use these patterns behind trajectories to detect incidents. In the offline discovery phase, first we extract incident speed vectors from trajectories that pass through incident locations when an incident occurred. The corresponding normal speed vectors are obtained by taking the average speed of these vehicles, which pass through the same road segments and the corresponding time points. We then discover incident patterns from these two kinds of vectors. In the online detection phase, we match the pattern for trajectory T with incident patterns we discovered in the offline discovery phase. If it can be matched, then incident is detected. Otherwise, no incident happened. In figure 2, we illustrate the trace of one vehicle passing through the incident location from road segment R0 until R10 in the road network, where the sequence of black dots PTI represent one trajectory, and the black explosion mark stands for an incident. For each road segment Ri, we have a time Ti when the vehicle passes through Ri and a corresponding speed Sriti. To get the normal speed on Ri at Ti, we aggregate the trajectories which passed through Ri at same time without being involved in any incident. Our idea is to discover incident patterns by comparing the incident speed vector and the normal speed vector as the incident impacts the speed of vehicle which passes through the incident location. In figure 3a, the dashed line represents the normal speed vector, while the solid line represents the incident speed vector. In figure 3b, the line represents the candidate incident pattern, which is obtained from the difference between the normalized normal speed vector and the normalized incident speed vector. From figure 3b, we can see that the candidate incident pattern first increases in trend, then fluctuates a little, and finally decreases. The first step of our solution is noise filtering. We filter out incident vectors which are similar to their corresponding normal speed vectors. This step is necessary as not all vehicles passing through an incident location are actually negatively affected by the incident. We use parameter delta to filter noise. The second step is incident pattern discovery. First, we give the formal definition of pattern. We define it as the difference between normalized incident speed vector and the normalized normal speed vector. Then we group patterns of all incident cases into key clusters. The centers of these key clusters are chosen as the incident pattern. In online detection phase, we trace the pattern PT behind the real-time trajectory T by measuring the distance between it and the key incident patterns. If there exists one incident pattern PAI such that its distance to pattern PT is smaller than the predefined threshold gamma, then we detect an incident. We evaluate our method on two data sets. The first one is real-world data set from Hong Kong. In this data set, there are over 35 gigabytes of trajectory data collected from 440 taxis in Hong Kong in 2010, and it contains over 4,000 incidents. The second dataset is simulated dataset from Beijing. We simulated GPS data and incident data within the second ring road in Beijing using simulation software SUMO. We simulated over 4 gigabytes of GPS data and 5,000 incidents. We evaluate our method on two data sets. We evaluate the effectiveness of our method on two data sets, HK and BG, over 4 metrics: F1 value, detection rate, false alarm rate, and mean time to detect. From table 3, we can see our FDM method achieves the best F1 value, false alarm rate, and mean time to detect, and gives a relative higher detection rate. From table 4, we can see our FDM method gives the best F1 value, detection rate, false alarm rate, and mean time to detect. This is all about our work. Thank you for your time. Bye.